What we're going to start today is fault-free analysis. So most of the time you will see me, I'm saying it as FDA, fault-free. Now first I will take you through the definition of faulty analysis, and then I will show you how we perform various analysis on FTA. Now what is the definition of FTA? It is a top-down graphical technique investigate either qualitatively or quantitatively. Quantitatively. How components of a system can cause the system via logical relationships. For those of you who are joining us now, we are starting the faulty analysis, FTA. It is a graphical technique to investigate either qualitatively or quantitatively how components of a system can cause system failure via logical relationships. FTA identifies all possible causes of a specified undesired event. Now this undesired event in faulty analysis is what we call as a top event. I will also explain it in a couple of next slides. This is called as the top event in a faulty analysis. to go to the next slide, please. Now, because I'm saying it is graphical techniques, there are some symbols that we use in faulty analysis. Now, I'm going to mention some commonly used symbols in fault tree analysis. There are many symbols, some commonly used here. Now, the first one are the logical gates. As I said, there will be logical relationships. So we have some logical gates. Now, two important logical gates that we need to study are AND gate and OR gate. Now, AND gate is drawn something like this. And here you have the inputs in the AND gate, and here you have your output. Now, the OR gate is drawn something like this. It is a curved shape, not the straight. It is not the best drawing, but it shows the meaning. Inputs, and this is my output. We use these AND or OR gates. When we are defining the AND gate, the output event is generated if and only if now here the important word is all. If and only if all input events are present. Or I can say when all input events fail. That is where we use our AND gate. However, if there is one input fails, that is where we use our OR gate. That's what we will define for our OR gate. The output event is generated if, now the important word here is at least. If at least one of inputs is present. or I can say at least one of input events fail. So the AND gate is used when we have all inputs failure. This is the keyword here. And OR events occur when we have at least one input failure. That's where we use our OR gate. Now the definition of the AND gate is similar to what you have studied in your for the parallel systems. Parallel systems. And for OR, this definition is the same as you have studied for the series system. Folks, I need to go to the next slide, please. Now the other symbols in FTA are the basic event. This is used for the basic event. This symbol is used for the basic event. It is also called the primary event. How do we define this basic event or the primary event? These are the primary causes and cannot be further divided. Or we can say these are the root causes. So if we cannot divide an event further, that is called as a basic event. Or the root cause. This rectangular shape it has an output and the input. This is called as the intermediate event. Intermediate event. How we define it? A fault or event caused by a combination of other events via logical gates. I will take an example in the next couple of slides, and these will be clear to you, all these symbols. So the logical gates that we are studying are AND gate, and we are studying the OR gates only. Now for the top event, the symbol that we use is this one. This is rectangular, and there is a called, this is used for top event. Or I can say this is used for the undesired event. Just keep in mind the fault tree analysis, FTA is used for the failure, to identify the failure of the system, not the success. Folks, I need to go to the next. Now, if you have any undeveloped event, this is the symbol that we use for it. This is used for undeveloped event. By that, I mean to say any event which is lacking some information. How we define it? A fault that cannot be subdivided more due to lack of information. As soon as the information is available, we build up the next events in this. Now there are some procedure steps for the fault tree analysis. What is a procedure to develop a fault tree? Procedure steps. The very first step is we need to define our top event. Let's say I give it a name of TE. Now, as I mentioned earlier, the fault tree analysis is used for the system failure. This top event, it consists of system failure. The second step is step number 2. We define those events which directly contribute to the top event or the system failure. So what are the steps? The first is we define our top event. The second is we define those events which directly contribute to the top event or the system failure. Folks, I need to go to the next slide, please. Now I'm going to take two examples to elaborate these two steps. For example, I know that my top event is the system failure. So this is the symbol that we were using for our system failure. If I put down inside this is my system failure. System failure. Now we'll take another example with the same system failure. This is my top event. This is a sample for my top event. And this is my system failure. Now, if I have the information, let's say I say that just leave some space here. If there are two events, E1 and E2, if I say E1 fails or E2 fails. Now, how we construct this in the fault tree? If E1 fails or E2 fails. Now, as you can see, I have either option. So E1 can fail or E2 can fail. According to the definitions that I mentioned in the previous slides, we will be using the OR gate here. Now I will draw my OR gate here because the information is showing me that either E1 can fail or E2 can fail. This is my OR gate symbol here. And for example, these events can be further classified, so I will take them as intermediate events. And for the intermediate events, we use our rectangular. This is the rectangular symbol that I drew previously. So I will say it as E1. And I will use the same one for E2. Now, second scenario could be if both should fail, both E1 and E2 should fail. Now, in this case, I know that this is a failure of both of them. So in that case, I will use my. So these must be connected using the AND gate now. Depends on your problem statement. This is my symbol for the AND gate. And the rest of the procedure remain the same. This is my E1 and this is my E2. Now, as I mentioned previously, this OR gate use is similar if we draw a series system where we have, let's say, E1 and I have the E2. Now, for example, these are two electric lights and this electric light does not work, so this means E2 will also not work. Now in case of the AND gate, we have the parallel systems. This is my E1. This is my E2. This is what is denoting a parallel system. For example, these are the valves, and here we are interested to find out either the water comes or not. This is the water supply line, and if both of them are closed, only then there will be no water here. If this one is open, this one is closed, the water can have here, or the vice versa. Folks, I need to go to the next slide, please. Now the third step is to continue this procedure until desired level of details is now this step means the event that we have previously, we will just further subdivide them. So for example, if E1 was linked, it was your intermediate event, it is linked through A and B, and your E is linked using C and D. How do we show them in the fault tree? So we start with the top event. This is my system failure. I have my OR gate here. The OR gate. It is linked with the intermediate event of E1. And the second event is E2. They are linked through OR gates. Now we know that our E1 has the basic events of A and B. So these should be connected using the AND gate further. This is my AND gate. And they are connected with the A and B. Now in this example, I'm assuming A and B cannot be further subdivided. So this is why I'm taking A and B as the basic event. And for the basic event, you know that we have a circle for them. Because these are the basic event, these cannot be further subdivided. Now similarly, we know for E2, have C and D as the basic events. So I will connect them using AND gate. It is a basic event, so I can have a circle here. And D is the basic event, I can have a circle here. Now the shape of your fault tree will vary from problem to problems. So just write down here your A, B, C and D are your basic events. Now, how we perform the quantitative assessment here. If you have OR gate, we use the union between those events. If you have events connected through AND gate, we use our intersection properties. This is what I'm going to show you in the next slide. Folks, I need to go to the next slide, please. Now, as you see here, my top event is a system failure, and this is connected to E1 and E2 using the OR gate. And we know that for the OR gate, we will have union between E1 and E2. That's what I will do in the next slide. Now, the probability of your top event, because E1 and E2 are connected using the OR gate, it will be the probability of E1 union of E2. And this is the formula that we used previously for the intersection. I can open it as the probability of E1 plus the probability of E2 minus the product of probability of E1 times the probability of E2. Now in mathematics, we can journal as 1 minus. This is the symbol that we use for multiplication. Multiplication from 1 to 2 of 1 minus probability of your E event. Now this symbol is for multiplication. Do not get it confused with the gamma function. The gamma function finish halfway. That's what is the gamma function. But we are not using this here. We are using the multiplication. Once you expand this, you will get 1 minus the probability of first event times the 1 minus probability of your second event, E2. Now I will take you back to the fault tree and would like to show you something. Now if I want to find out the probability of this E1 event, I know A and B are connected through AND gate, and for the AND gate, I know I need to use the intersection. So this is what I will do in the next slide, and similar approach for E2 variable. So the probability of your E1 event, this is equals to probability of A intersection of B, because these are the basic events here. And for the intersection, we just multiply the probabilities. Probability of A times the probability of your B. Now E2 is also connected through AND gate. So I will have the probability of E2 equals to the probability of, now E2 has the basic events of C and D, C intersection of D, that should be equals to your probability of C times probability of E. Now I take these values of probability of E1 and E2, and I'm going to put them in, let's say, equation number 1 here. So the probability of my top event will be equals to, now this probability of E1 is my product of A and B. This is the probability of A times the probability of your plus probability of E2. This is the product of probability of C and D. Probability of C times the probability of D, and minus the product of these two probabilities of E1 and E2. So I will have the probability of A times the probability of B times the probability of C times the probability of D. So this is how, for the given fault tree in our examples, you can find out the probability of your top event failure. Folks, I need to go to the next slide, please. In FTA, there is one thing which is called as the minimal cut set. This is also called as the MCS. First, I will define it and then I will take you into the details of this. It is a set of minimum number of primary events that produces the top event if and only if all the events of the set occur. Now I'm going to take an example of another fault tree. For example, this is my top event, and it is connected using the AND gate to E1 and E2. And we further classify E1 into A and C. This is a different example than what we were doing before. And it has two basic events, A and basic event is C here. For E2, for example, there are basic events of B and D, and they are connecting using the OR gate. So this is my B here. And this is my D. Now the minimal cut set, MCS. When you're writing the MCS, we just make the combination. For example, I can combine A with the B. It will be the product of A and B. This is basically written as the product of your probability of A times your product of probability of B, if they are independent. Now the second could be, I can combine A with this D. So let's say give it a name of 1. The second minimal cut set could be, I can have A and D. Now the third combination could be, I can combine C with this B. The fourth combination could be, I can have C combined with Now these are called the minimal cut set of our given example. Now you might be thinking that we can have minimal cut set of A, we combine A, B and C as well. Now, it's not your minimal cut set. That's because the C here, this C is redundant because system has already failed because of the failure of A, as we are connected through the OR gates. So this is not the minimal cut set. That's because system has already failed. A C is the redundant. Now the same can be true with the A even. You can, if I have A, B, C, we can say that A is redundant here. So this is also not the minimal cut set because system has already failed because of the failure of the C here and the B here. By system failure, I mean to say the failure of the top event. This is also not the minimal cut set. Folks, I need to go to the next slide, please. Now, I'm going to draw a diagram, a fault tree diagram, using these minimal cut set. So here I have the same top event. Now I had 4 minimal cut set from my previous example, and those were minimal cut set 1. Now it is an intermediate event because it was further divided into A and B. we have the minimal cut set 2, we had the minimal cut set 3, and then we had minimal cut set 4. Now what is the logic here? The failure of this or this or this or this can fail the, so that's why they are connecting using the OR gate. So I'm going to connect them using the OR gate here. So this is my OR gate. This is connected to MC1, MCS1, MCS2. This is connected to MCS4, and this is connected to MCS3. Now if I take you back here, for MCS1 I have two events, A and B. So these two basic events should be connected to MCS1 using the AND gate. So here what I'm going to do, I will be using my AND gate. This is my OR gate, and this is my AND gate here. And I will have the basic events. Because they are basic events, I'm going to write them in the circle. This is my A, this is A, and this is my B. Now in terms of MCS2, I will take you back to slide. I have the events of A and D. So I'm going to connect them using the AND gate. Here I have A and D. Now the similar logic is used for the next two. This is your AND gate here. For MCS3, I have C and B as the basic events. For MCS4, this is my AND gate, and they were connected using the C and D. Now either you find the probability of this fault tree, the top event probability of this from this fault tree using the MCS, or you find the probability of this top event using this fault tree. Both of them will have the probabilities. So both fault trees have same probability of top event. Folks, I need to go to the next slide, please. Now in the next slide, I'm going to perform some calculations here. Let's assume I assign some values here. So for example, I say that in this fault tree, the probability of my basic event A is 0.1. For C, my probability is 0.2. For B, let's assume the probability is 0.1. And for D, this is 0.3. So I'm going to perform the calculations here to find out the probability of my top event. Folks, I will go to the next slide, please. So my probability of top event, this is what we figure out. That should be the probability of A union of C, because it was connected through the OR gate. And we just figure out that this is A intersection of C. And if the events are independent, this one should be equals to product of their probabilities. Now this one I assigned it a value of 0.1 here, plus this one I assigned the value of 0.2 in my fault tree, and then take the products here. Once you solve it, you will get 0.28. Now similarly, when you perform it for your E2, the answer will turns out to be 0.37. Now for the top event probability, we have probability of E. Because they are connected through E1 and E2 are connected to AND gate, we will use the intersection here. This is for the AND gate. And the intersection is solved by taking the product of the probabilities. So it will be probability of E1 times the probability of your E2. Now the E1 probability is 0.28 times the probability of your E2, which is 0.37. And you get 0.1036. This is the probability of your top event failure. Folks, and to go to the next slide, please. For minimal cut set, two things are important. The first is the rank of a cut set. This is defined as the number of primary events of minimal cut set. the lower the rank, the most critical minimal cut set would be. By that I say, for example, I have two minimal cut sets. Minimal cut sets of A and B. And another minimal cut set is, for example, this is A, B, C, and D. Now the rank of this minimal cut set is 2, and the rank of this minimal cut set is 4. Now we will say that the most critical minimal cut set. By that I mean the most critical minimal cut set. I mean to say the S1 would most likely to fail top event, or your minimal cut set 1 has the most influence on top event. And how we decide it? We look for the rank of your minimal cut set. Here the rank is 4 because variables. Here the rank is 2 because we have 2 variables. So if you have the lower, the most critical your minimum cut set would be. Folks, I need to go to the next slide, please. Now the second important thing is the importance measure. Importance measure of a minimal cut set. How do we define this importance measure? You have the importance measure, let's say for I, that is equals to the probability of your minimal cut set I divided by the probability of your top event. Now I will take an example here. For example, you want to have the probability of minimal cut set and it is the product of your A and B, for example. I take them as 0.1 times 0.1, and we get 0.01. And there is another minimal cut set, for example, which is MCS2, and that is the product of the probabilities of A and D, for example. And for example, it has the probabilities of 0.1 times 0.3. So these are the probabilities of your MCS1 and MCS2. Now I want to find out the importance measure for each of them. So let's say this is IM1 here, and here I'm going to do for IM. Now this is the IM1, so I need to use the probability of my MCS1, which is 0.01. And then I divide it with the probability of my top event, which we just find out is 0.1036. You get the answer of 0.0965. This is my IM1. Let's calculate IM2. So in IM2, I have this probability, 0.03, divided by the, if the top event remain the same, because it is for the same fault tree. So my IM2 is 0.29. Now, the interpretation of this result is that our minimal cut set 2, now this value, is higher than your IM1. So your minimal cut set is more, minimal cut set 2 is more critical than minimal cut set 1. Again, by critical, I mean to say this can cause the failure event MS2. Now, if you compare these two values, this value is 3 times more than your IM1 value. So I can say that my IM2 is 3 times more important than IM1. Go to the next slide, please. Now, if you want to find out which event is most influenced to the top event, now to find the contribution of each basic or primary event to the top event we have four methods. We have four methods. The first one is Fussell-Wesley importance. This is also called FV importance. The second method is the risk reduction worth. This is also called as RW. The third one is risk achievement. This is E. Risk achievement worth. This is also called as RAW method. And the last method is Birnbaum. Importance measure. It is also called as the BM method. Folks, I will stop it here and take your questions. In the next lecture, we will start all these four methods one by one. If you have any questions, you can ask me, please. Now, all this that we are studying in the fault tree analysis in particularly, we are doing a textbook. The title of the textbook is Assessment of Power System Reliability Methods and applications. Methods and applications. It is written by Marco Sipin. Marco. Now, whatever we are studying for the faulty analysis, you need to look on chapter 5 of this book. Chapter 5. Now, for your convenience, I will provide a PDF copy of this chapter. When I upload this lecture, it will be available over there for you. So you don't have to spend your time to find out this book and the chapter. You are welcome. Is there any more questions for me, folks? It seems like you don't have any more questions. So I will just let you go. Go through this lecture and read this chapter. We are not done with the FT, of course. We need to work on these 4 methods and learn about them more. We will do that in the next lecture on Tuesday. Yes, Jacobo is saying I need to digest the notes. Yes, definitely. You can have it. And if you have any question, please drop an email. I will be more than happy to assist you. Thank you very much, everyone, and have a good weekend. Thank you.